So we're going to start off by looking at 5 basic limit laws, and we're going to use these to help us break down more complicated functions and find limits of the smaller parts. So these limit laws are in your textbook in section 2.3. So if I go to the e-text, here's the box with the limit laws. First law is telling us that if we have the limit of the sum of two functions, we can find that by finding the limit of each function and adding them. And the same goes with subtraction. So let's look at this function. Here's an example. Another way to word this law is the limit of the sum is the sum of the limits, or vice versa. It applies with difference too. So looking at this, the limit of this function as x approaches 1, this law is telling me that I can break this up into two limits, the sum of two limits. So I can apply that law that used the terminology f of x and g of x. I'm saying, okay, let's call g of x that first term and f of x that second term. I can find the limit of each function. So I still need to use a graph to do that at this point. So here's g of x equals x squared. And the limit as x approaches 1, if I follow along the graph as x approaches 1 from both sides, right and left, I see that the limit is 1. And then my other function, this rational function, the limit as x approaches 1, I have a hole at x equals 1, but that's okay. The limit is still 2. So therefore, I can just add these individual limits and my answer is 3. And we can verify that graphically. So this dashed graph is the actual graph of the sum of those two functions. So now the next law, we had the sum, we had the difference, now it's multiplying by a constant. This next law tells you that you can take the constant, pull it out of the limit. So you can just find the limit of a simpler function and then multiply it by that constant. So if we look at g of x equals 3x squared, what this law is telling us is if we take the limit as x approaches 1 of this function, we can just pull that 3 out and look at the limit of the simpler function as x approaches 1 of x squared. Well, like we saw from the previous slide, the limit as x approaches 1 of x squared is just 1. So this law is telling us that we can just multiply 1 by that constant c, and our limit is 3. And it makes sense that, when you multiply a function by a constant, if you recall from pre-calculus, you are doing a vertical stretch. So as your x-coordinates are approaching 1, the y-coordinate is just 3 times the y-coordinate of the function f of x equals x squared. So it makes sense that the limit is just 3 times the limit as x approaches 1 of x squared. The next law is the product law. So that's telling us the limit of the product is the product of the limits. And if we look at this example, we can see how this would come in handy because you don't really want to have to multiply this out. So let's look at the limit as x approaches 1 of this function. This law tells us that we can look at the limit of each of these factors and then multiply those limits. So if f of x is this first factor, and we call g of x the second factor, x to the 5th plus x squared, I'm just taking that, I'm finding the limit of each factor. And again, we're going to need to look at the graph to see what these individual limits are. So this is x to the 4th plus x plus 1. This function is g of x, is x to the 5th plus x squared. And if you look at the individual limits, you see as x approaches 1 for g of x, the limit is 2. As x approaches 1 for f of x, the limit is 3. Therefore, the limit of the product is just the product of those two limits, or 6. And we can verify that by actually graphing the product function. So it's this dashed graph. I can see that as x approaches 1 on the product function, the limit is 6. And you can look at it numerically too. The next one is the quotient law. So the limit of the quotient is the quotient of the limits as long as the limit of the denominator is not 0. So again, let's look at this example. The limit as x approaches 1 of ln of x plus 1 over e to the x. Well, this law tells me that I can find this limit by looking at the limit of the numerator and denominator separately, right, and then performing the division. So I can use this here because e to the x, recall, is never 0. So it's not a problem to use the quotient law here. So again, I need to look at the graph to find these limits. So if we look first at the numerator, ln of x plus 1, that's this graph. And I can see as x approaches 1, that graph approaches y value of 1 as well. And the limit as x approaches 1 of e to the x is 2 point something. It turns out it's 2.7-ish, or 2.718, which is an approximation of e to the first. So therefore our limit is 1 over about 2.7, which is about 0.368. Here we feel a little bit better verifying it graphically and numerically because e is not kind of a natural thing that we're used to working with every day. So this dashed graph is the quotient, and you can see that as x approaches 1 from the left and right, the y value is 0.368.